Hello, everyone. My name is Carolyn, and we are going to continue our discussion about the normal curve. We were introduced to it in my last video. In the last video, we also talked about the z-score. In this video, we're going to be talking about the areas under that curve and how we can use them to calculate probabilities. We will see a real-ish example at the end of this video. We're going to start though with the standard normal curve. So remember some of the things, first of all, about the normal curve. It is about a random variable that can take on any values from negative infinity to infinity. Now, granted, some of the very edges will have very small probabilities, but this way we're allowed to kind of cover all of our bases. It is a distribution curve. It's symmetric. It is bell-shaped, and it will be centered around the mean. So, and if you can remember the mean, the symbol we use for the mean of a population is mu. And that's that wonderful little U that we have sitting here. It is always above the x-axis, as is any density curve used to calculate probabilities, because our probabilities cannot be negative. We also have the total area under this curve is equal to 1. Because it is a density curve, all of our probabilities have to add up to 1. And in continuous situations, the area under our curves represents that probability. So we have to have a total probability of 1, or a total area of 1. We have some inflection points, and I'll talk about those a little bit later. Inflection points are something that you can learn about in calculus class. And in this case, they happen to be one standard deviation from the mean in either direction. It's basically something that talks about the shape. An inflection point is a place where a curve will go from being concave up to concave down. What we mean by concave up, it's kind of like a bowl. If you want to think about a bowl that holds water, concave up means it's going to hold water. So it's got that curve that's kind of going up. Concave down is going to be kind of like almost like an umbrella shape. So you'll see that little umbrella. So concave up kind of has this shape, concave down, kind of that shape. And it could be, and an inflection point is a place where it changes from being concave up to concave down, or vice versa. So the first standard normal curve we're going to look at is one that was standardized. So it's basically taking a general normal curve and standardizing so we can kind of find an even center place to kind of take all of our normal curves to. And we can do some mathematical transformation to get to this standard normal. In fact, the z-score is the way we travel from a normal distribution or a other normal curve to the standard normal. We go through that small transformation called the z-score. But we need to kind of look at what this standard normal is. I say it's man-made because I have not come across anything that is centered at 0, that has a mean of 0 and a standard deviation of 1. So that is our standard normal. It does have a mean of 0, so it's going to be centered around 0, and it has a standard deviation, which is this really nice number 1. So we're going to look at our curve. I have a nicer picture of it here. So there is our standard normal centered at 0, and we have the standard deviation is equal to 1. So standard deviation going one direction in either place. And if I went that 1, these two places right here is where we have those inflection points, where it kind of changed from being concave up to concave down. Sometimes hard to tell exactly where that happens. You would need calculus to actually do that, to find those places, but it is just something that does happen. The inflection points will be one standard deviation in either direction from your mean. Also helps us draw a nicer looking curve. However, my curves, as I've stated before, always look a little wonky, not so beautifully centered. They're not always symmetric, but it doesn't matter. I usually draw them just to help me get a feeling for what I'm looking at. Okay. When we're working with this normal curve, I want to also remind us that these do continue to go on and on and on. However, a lot of times we only will label 3 in either direction, mostly because if you go beyond that, we have such a small amount. So, and Z is the letter that we like to use when we're dealing with this standard normal. We like to use X in some other cases, but we save the letter Z for our standard normal because we talk about that Z score. So if you see the letter Z, when we're talking about probabilities of Z being between here and there, we're referring to the standard normal curve. It turns out that, and again, these were all calculated using calculus courses. And actually, it was a Calc 2 or 3, depending on where you're going to school, to calculate them. However, we don't need to know calculus to find them. We are going to just use those results. It turns out that we have this thing called the empirical rule. And the empirical rule basically has 3 pieces to it. And what it says is that if we have the data, people, cans, whatever, that roughly 68% of our data will fall within 1 standard deviation from the mean. So for our standard deviation, what that means, or a standard normal, what that means is the probability that you're between -1 and 1 is 0.68. In terms of my picture, that means if I had all my people or all my things sitting under this curve where you situated, we would have 68% under this curve right there. So 68% of our data is there. That's more than half. So that's a lot of our data. If we continue this and we go between 2 standard deviations from our mean, so we go 2 below and 2 above, we're going to pick up and have a total of 95% of our data. So in terms of a probability statement and the standard normal, we're going to have -2 to Z to 2 is 0.95 or 95%. So on our picture, look at it this way, we get 95% between in this region, which means we only have 5% outside of those places. And the last step says, well, what happens if I go even a little bit further? If I go within 3 standard deviations, we pick up 99.7% of all of our data is going to be within 3 standard deviations of our mean. Now, these numbers, this 68, this 95, and this 99.7 are not exact values. They are approximations. They are pretty close. In another video, we will actually find out what the more exact versions of those values are. But they are pretty darn close, 68%, 95, 99.7. So in my picture, if I go from -3 all the way from here, maybe I'll just do it all the way to here, my picture's getting crowded here, I get 99.7. Some places when you read this empirical rule, they will refer to it as the 68, 95, 99.7 rule for obvious reasons. We get 68, 95 if we're going 2, go down 3 and up 3, we get 99.7. 68, 95, 99.7. Okay, but what if we wanted to know the probability from 0 to 1? So I'm going to draw a little picture. I'm going to also use this guy a little bit too, but I'll kind of be back and forth between them. So picture from here. So there's my normal curve. We're talking about Z, so that is my standard normal. I'm going from 0 to 1. So we're looking for this region here. Let's kind of color that in yellow. Okay. The answer to that is we're going to look at our original. And if I went from -1 to 1, we got 68%. This is part of that or half of that. So I can take that 68% and divide it by 2, which is 34%. And the reason I can divide it in half is because my normal curve is symmetric. If it wasn't symmetric around that center, I could not do this. So the probability from 0 to 1 is 0.34. Remember, probabilities are always a value between 0 and 1, so we will state it in its decimal form. You can interpret it, though, as representing 34% of our data. But if we're talking about a probability, it's going to be 0.34. We're going to do another one. I do quite a few of these, just so we can kind of manipulate the fact that it is symmetric. And here we're going this time from -2 to 0. So going from -2 to 0. And I'll highlight that area. Now, if you remember from the empirical rule, roughly 95% is from -2 to 2. So there's 95%. So we're going to take half of that because it is symmetric. So 95% divided by 2 is going to be 47.5% or 0.475. Okay. All right. What if I wanted to go from 0 on up? So here's my curve. Standard normal. Whoops. 0. Let's put in my 1, my 2, and my 3. My -1, my -2, my -3. And we want to go from 0 up. So this. Okay. That is half of my graph. Now, remembering that the total area under our curve is 1 or represents 100% of our data, this upper half would represent 50% of our data. The lower half would represent 50% of our data. So the probability we're in the upper half would be 0.5. Remembering probabilities are between 0 and 1. I have 3 more here for us. And then I'll kind of have a table that shows us all the results. So we're going to this time go from a -1. And there are a couple of ways to do this one. So we're going to go from -1 up to 3. That's what my probability statement says there. Okay. And the way I'm going to do this is I'm going to divide it into a couple of pieces. Now I can't take like -3 to 3 and chop it up into, 6 pieces and then multiply it by 4, because notice if I just look at this piece here compared to this piece there, they do not have the same area in them. These two do. These two are equal, but these two on the ends are not. So what I'm going to do is I'm going to use that empirical rule, and I'm going to calculate this area here from -1 to 1. Remembering that is half of our 68. So that is my 34 that we calculated before, that 0.34 or that 34%. Now from -3 to 3 is 99.7. So from 0 to 3 would be half of that 99.7. So I'm going to take my calculator to help me a little bit. Some of those other ones I could divide easily by hand. So that's going to give me that 49.85%. And now thinking in terms of probability, probability is the area under the curve from here to here. I need that total area from -1 to 0, and then again from 0 to 3. So I'm going to add those two pieces together. Since I'm talking about a probability, I will do it in decimal form. That's an 8.5. And so I will have 0.8385 if I add those two together. So if I was talking about what percent of my people are in there, or what percent of my whatever I'm looking at are in there, I'd have 83.85% of my data is in that shaded region. Okay, just a few more. All right, so now we are going Z is bigger than 3. Okay, so here's my 0, 1, 2, 3. And we're looking for this really little upper tail. Now, usually isn't quite this high, so just kind of I draw my pictures so that you can kind of see them. So here's my -1, my -2, my -3. Remembering from -3 to 3, according to the empirical, we get roughly 99.7% of our data. So that means the rest of our data is outside that region. Now, also thinking everything is 100%. So if I took 100 minus the 99.7, that's going to give me 0.3% in both of these tails. So that would be my green region there. I just want the upper one, so I'm going to divide 0.3 by 2, and I come up with 0.15. Notice this is a percent. So as a probability, that's going to be this percent in decimal form, so 0.0015. So a very, very small chance of getting into those tails, because we have most of our data within 3 standard deviations one way or another. Also think about it then, if you calculate a standard deviation and get 5 point something, that means we are way above that. I mean, the chances of getting that is very, very slim. So you are kind of pretty much an outlier. And that's another way to kind of judge if you are an outlier or not. A lot of times they will set up some boundaries, either the -2 to 2 or the -3 to 3. And anything outside of that is considered an outlier, and very slim chance of those happening. We're going to do one more example before I show some results here. Okay, get it to zoom in here. So we're going to go from -1 or from 1 to 2. That's going to be a little bit more difficult. So we'll draw a picture and see if we can figure this out. Okay, so we're going, here's my 0, here's 1, and here is 2. So we're going from here to here. And I'll color that in yellow. Okay, so negative from 1 to 2. Sorry, that doesn't show up very well. Let's zoom in a little bit there. All right. So I want to think of some things here. From here to here is 68. Or you could think of from here to here, we've already done is 34, right? I'm going to use that, I think. We also did from -2 to 0, which would still be the same from 0 to 2. So we also did from 0 to 2 as being 47.5. So from here to here is 34%. From here to here is 47.5%. And I want to know from here to here. That's my question. The way I can do that is we can subtract. Because if you think, we can't like take this and divide it in half, because this area, even though the base is the same, this is taller. So we'd actually have more area in that 0 to 1 than we do from 1 to 2. So we can't just take this 47.5 and divide it in 2. We have to actually subtract the 2. Because if I take this and I get rid of this part, I will have that piece left. So we're going to take that 47.5% subtract my 34%, and I come up with 13.5% or 0.135 in terms of a probability. And we can do that for almost any section between the 0, the 1, the 2, and the 3. I'm not going to do that in this video, but I will show you the results. The results are here. So if you think, just let me back up here, zoom out. There we go. So we can get the whole picture. Like, sorry for it being a little blurry. My camera is not the best, but we have, again, 68% from between -1 and 1. Dividing that in half gave us the 34 and the 34. Taking the 95 from -2 to 2, we found that 13.5. That was just in that last example. So, and again, it is symmetric, so 13.5% on both sides. I could have done 2 to 3 similarly, that I did, and I could have used the 0 to 3 and the 0 to 2 and done some subtraction, and I would have gotten 2.35%. And then we also did do a tail, these little upper tails. That was our 0.15%. If we did them in terms of probabilities, this would be 0.34. I'm just going to do the upper half, 0.135, 0.0235, and 0.0015. So depending on what the question is asking you, you will use either the percentage or you'll use the decimal. If it's asking for probabilities, it will look, you'll use the decimals. If you're using, asking for a percentage, you will use that percentage piece. Okay, let's take this, and that's pretty much it for the standard normal, but what happens if we move away from the standard normal and talk about any normal curve? Well, that empirical rule still applies. And it just have to be a little bit careful. If you go, we'll have 68% if you are within 1 standard deviation from the mean. So what that means is if you take your mean, so your mean is a number, and you add 1 standard deviation and subtract 1 standard deviation, you will get 68% of your data, or the probability will be 0.68. If you add, so here's your mean, and you add 2 standard deviations and you subtract 2 standard deviations, that's what this does here. So you're adding and subtracting 2, so 1, 2, you're going to get 95% of your data. If you go and add or subtract 3 standard deviations, boom, 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 we're going to get 99.7% of our data. And just like we did before, we could split them all up and do all the pieces. We'd still get those 34s and that 13.5 and the 0.15 on the very, very tails. So we can use this table as well in general. So, okay. I also want to remind you that if you find a z-score and you get like a z-score of a 1.3 or a -1.3, that's telling you that we are that many standard deviations away from the mean. So if I got a -1.3, that means I'm in this region here, because 1 would have been right here, -1. I'm a little further than that, but I'm not to -2. So -1.3, this is kind of where I would be located. Gives you an idea, helps you picture where you are in that normal curve. But we will talk more about that as we go. Actually, and if I had found the z-scores for these values, and we'll do that for an example, you will see that it does go to the 1, the 2, and the 3 from in that standard normal. So we're going to do an example here. And I'm going to use that table that we just did to actually get our questions. But here's my example. We have the head circumference of a newborn baby. Okay, and I made these numbers up, so these are not factual values. This is just for illustration purposes only. But let's suppose that a newborn baby's head, the size of its head, it has a mean of 11.8 and a standard deviation of 1.5 centimeters. So we want to find the probability that a newborn will have a head that is smaller than the 8.8. Okay. And so what I'm going to do is I'm going to find those little boundary values that set up the boundaries for the empirical rule. I like to refer to them as the magic numbers. They're the ones, the twos, and the threes as we go. So I'm going to kind of just draw my normal curve. And I can draw a normal curve because in the problem it said it is normally distributed. What that means is the size of a baby's head follows this normal curve. Okay. Again, my normal curves are a little bit wonky. They always look the same, but I do know it's going to be centered around the mean. The mean was 11.8. The standard deviation of 1.5 is going to tell me how spread out or how steep this curve is. A 1.5 is a little bit bigger than 1, so it's going to be a little flatter than your standard normal curve because it is a little bigger. Remembering bigger means more spread out. Now I'm going to add and subtract my standard deviation to get that 68, the 95, and the 99.7 boundaries. Because if I go up one standard deviation, so I'm going up 1.5, so if I take 11.8 and I add 1.5, I get 13.3. That would be one standard deviation above. If I go down that amount, so I'm going to subtract 1.5, that's going to give me 10.3. I'm going to do that again. I'm going to add my 1.5, so that's going to give me 14.8. I'm going to do it one more time to get the 3 in there, so to get that 99.7 mark, that's going to give me 16.3. So I'm adding 1.5 each time. I'm going to subtract 1.5 each time to get my -1, my -2, and my -3. So that would be 7.3 right there. Okay, so here is that, if I put these little boundaries up here, here's that 68%. My 95%, and my 99.7%. Sorry, it's not very symmetric as I drew these, but it's the idea. I'm going to take a couple of these and find their z-score. So remembering that a z-score is your data value minus the mean divided by your standard deviation. So let's just take the middle one first. So we're going to take our data value minus our mean is 11.8, and divide it by our standard deviation of 1.5. We do get 0. I'm going to take my 14.8, subtract off my mean, divide by my 1.5. That's going to be 3 divided by 1.5, which is 2. So this is my 2. This is my 0 and my 2. I'm going to try the 10.3. So 10.3 minus my 11.8 divided by my 1.5. That's going to give me a -1.5 over 1.5, or a -1. Because we added and subtracted our standard deviations, this will turn into the 0, the 1, the 2, and the 3, the -1, the -2, and the -3 from that standard normal that we talked about. So it helps us picture where everything is. Okay, now we can actually go back to our question and answer it. We wanted to know, what is the probability that this head circumference of a newborn will be smaller or less than 8.8? So we're looking for the probability that X is less than 8.8. If I wanted to, I could transform this to the standard normal because it's going to be asking the same question. What's the probability that Z is less than 2? And what I'm going to do is I'm going to go back to that table that had all the pieces split up. Okay, so first of all, I'm going to highlight these pieces, right? Okay, and I'm going to look at my other curve here. So here's my two below right here. I'm looking at this piece and this piece. So I'm going to take those two pieces and I'm going to add them together. So I'm going to take that 2.35% and that 0.15%, and I'm going to add them together. And that's going to give me 2.5%, or in probability terms, it's 0.025. So 2.5%. I could have manipulated the 95% and things like that, but with the table from before, I have that. So now I can just use it. Okay, we're going to do one more. We're going to find the probability that a newborn will have a head circumference between 10.3 and 4.8. So I'm going to go up here. I'm going to shade this one in green and use the same picture. So 10.3 and 4.8. So that's kind of got like going a -1 up to 2, or 1 below and 2 above. So I'm going to bring out this guy. 1 below and 2 above. So here's 1 below and 2 above. So I'm going to take the 34, and the 13.5. And since we're talking about probability, it's the same as if I were doing a -1 to z up to 2. Those will both have the same pieces, 0.34 plus my 0.34 plus my 0.135. So I kind of wrote it all out here for you. So going from 10.3 to 14.8, or going from 1 below to 2 above, is my 0.34, 0.34, 0.135. Adding those all up, get my calculator here, turn it on, 0.68 plus 0.135, I get 0.815. So in terms of probability, it's a 0.815. If you asked what percent of babies would fall in that range, it would be 81.5% of all newborn babies will fall within that range. If these values were true, which they are not. I just made these up for illustration purposes. So none of my numbers when I do my examples are truthful. They are just all randomly made up values. So this brings me to the end of the standard normal curve, or the normal curve, and the empirical rule. The next video we'll talk about is what happens if we fall within those values. How do we find, let's say I wanted to go from here to here, which are not in that 68. I can't just take 68% because this height, even if this was in the middle, let's say I wanted to go from -0.5 to 0.5 in terms of the standard normal, I can't take these and divide it up. I can't take the 34 and divide it in half because this height is higher than this height. So these areas are not the same. Lucky for us, technology has all the answers for us. Before technology, it was done using calculus and put into a table format. And we did have to transfer every curve to the standard normal. So we could use one curve. We didn't have to have a curve for a table for every situation. We could just all transfer everything to that standard normal going through the z-score. But lucky for us, technology has erupted and we can use technology to have all those values right at our fingertips. So in the next video, we will talk about how do we use technology to just generalize any situation. But that'll be in our next video. So I hope to see you in the next video and for you to have a wonderful afternoon or day. Bye.